Hi everyone, I just wanted to finish part B on page 6 with you. I know we started in class. Just bear with me. I'm going to spend 30 seconds coming up with the given information and the need to find. The given information is they gave you they told you how quickly the radius is increasing. So that's why someone in class said it's the derivative of the radius with respect to time, and it's 2. Again, the word rate gives it away that it's a derivative. These units, they give away the independent variable, which is time, and the dependent variable, which is length. It's the length of the radius. They're asking for how fast. Actually, all of these problems will ask for how fast something is changing. This case, it's how fast the volume is changing. We're looking for how fast the volume is changing against the clock, so against time. So it's dt. How fast is the volume changing? When the radius is 1 centimeter long. That's what it's asking. So now I need to find a derivative. I need to find the derivative of volume. This is where the volume formula comes into play. I need a formula that I'm going to find the derivative of. I'm going to find the derivative of the left side and the right side. We are doing implicit differentiation here. My independent variable is t. This is not a t, it's an r. So remind yourself, is that r a constant? Is that r a variable? Is that r a function? That's what you're asking yourself. We know it's not a variable. The only variable is t. R is not a variable. We know it's not a constant. Like, I know it says constant rate, but the rate means that the radius is changing in length. If the radius is changing in length, because the radius is increasing. Every second that goes by, since we're blowing a balloon, the radius increases 2 centimeters every second that goes by. It is not a constant. The radius is not a constant. The radius is a function. This is why we need implicit differentiation. It's a function made up of t. So r, if you want to think about what r is some function. It's r of t. I don't know what function it is, but it needs implicit differentiation. Take the derivative of the left side and the right side with respect to t. So the derivative of v with respect to t. Here's the 4/3 pi. It is just a constant. It's the derivative with respect to t of r cubed. Okay, this is just the notation. This is just 4/3 pi. Now, we need to do the chain rule. I have an inside function, it's r. Imagine it's r of t raised to the 3rd power. Imagine that. My inside function is r. The derivative of r, it's just the derivative of r with respect to t. Again, the derivative of r of t is r prime of t. And instead of using the prime notation, I'm using that. My outside function is something cubed, like a cubic function, something cubed. Its derivative is 3 times something squared. So I just did the chain rule. The inside function's r, its derivative is that. My outside function is t cubed, something cubed. Its derivative is 3 r, you got to throw that back in, squared. I just did the chain rule. And I know it's weird. There is a derivative here, and I know that. This is where you start plugging in stuff. Notice how I did not use that 2. I did not use a r as 1. You are not plugging in any numbers until you found the derivative of both sides. I'm going to show you the strategies on this page. So I recommend writing down what you're given and what needs to be determined. Write an equation involving the variables whose rates of change are either given or to be determined. Our equation in this problem was the volume formula. Well, it's asking for how fast is the volume changing, so it's the volume formula. 3 says, differentiate both sides implicitly with respect to time, and the chain rule will be frequently used. Number 4, look at the word after. It's capitalized. After you find the derivative of both sides, that's when you substitute all the quantities that you know, that's when you substitute them into your derivative, which is the resulting equation. This is where you plug in chug because we're done with calculus. So 4/3 is going to stay, pi is going to stay. The derivative of the radius with respect to time, I'm so glad they gave me that. It's 2, 3 is going to stay. R, they want how quickly the volume is changing when the radius is 1, so it's just 1, and it's 1 squared is just 1. All right, simplify, and the 3's cancel, and my answer comes out to be 8 pi. Let's provide units so we realize this is the derivative. This is the derivative of volume with respect to time. It's 8 pi. Volume is written as centimeters cubed, and the time is in second. So this is showing how quickly the volume is changing based on time. A, we came up with the rate that volume is changing based on the radius. And again, if the radius is changing, because if you're blowing up a balloon, the radius is going to change. The volume is going to change. This shows how the volume changes.